work for Disney. The last year I was here, I said something like, we are not as cool as Pixar or Marvel, apart from us like owning them. But we just launched a new streaming service called Disney Plus. So I hope we are at least half as cool as they are now. By the way, the release was on Tuesday, so as you can imagine, the timing of this conference was like not that great for me. But I'm here and I have the slides ready. And now the topic of this talk, change data capture in distributed systems. As you can imagine, the system we built is massively distributed. We need to deliver content to millions of users around the world. And we have to track data changes among various microservices all the time. In this talk, I would like to give you a quick introduction into CDC, just in case you're not that familiar with this concept. I have a feeling that people are not as focused on this as they should be. And also, I would like to share my experience with CDC and give you some recommendations. Systems can be categorized into the source of the truth systems. We usually call them like primary stores. As an example, we can have a relational database with data about users, the place we go to when we need to update their name or addresses or doing various querying and things like that. Then we have derived or secondary stores, if you will. Data in these stores are derived from primary stores, often using various transformations. As an example from the user domain I just mentioned, we can cache user addresses close to the entry point of the system and show users different content according to it. And we would want to do that because our primary SQL store may not be able to handle the expected load, for example. So what CDC means, it's a little bit more generic, of course. It covers a lot of use cases. I will give you some samples later. The definition of CDC is that CDC is a design pattern that enables capturing changes to data and notifying actors so they can react accordingly. When thinking about CDC, there are a lot of things to consider. So let me give you some ideas. It's not gonna be an exhaustive list for sure, but it should be helpful. So let's start with reliability or tolerance to data loss. Essentially, are we fine if data in two related data stores become inconsistent? Or is this something which is like absolutely unacceptable for you? It very depends, right? Then we have scalability. Do we care if a system is able to scale with increased load or data size? Or we do believe it's not really needed? And now performance. Do we need our changes to be propagated to subscribers in real time? Or is it okay to wait a little bit? Consistency. Do we care about ordering of events, for example? Another thing to consider. And now fault tolerance. Is the system tolerant to failures? We may or may not want to introduce some redundancy to make it more resilient. I'm sure we could find many more, but I think this is like a good initial bash. When implementing CDCs, there are a few strategies how to do so. As you would expect, we have quite a few options. So let's start with probably the most obvious one. Basically, the records have a status attribute. Most commonly, it's a timestamp or a version number or something like that. This approach is very simple and can be used almost everywhere, as long as we can add this attribute. But there are certain reliability concerns, and as I will show you later, this approach is often combined with some kind of polling to check whether if any changes have been committed to the requested record. But I believe the different implementations are also possible. For storage engines that supports database triggers like MySQL or Postgres, we can implement store procedures triggered by various operations. Those can be used to seamlessly propagate changes to other data tables or even stores. Triggers are very reliable and fast, but may drain database resources, and they are not always available. The function essentially compares the current state of the data with the previous state of the data. The good thing is this is like very easy to implement, and it's like super generic. On the other hand, it requires a lot of resources to move the data around, and it cannot be performed real time. A lot of data storage solutions maintain a transaction log or a change log or an audit trail, if you will. Essentially the same thing. This is used for recording and tracking changes committed to the database in order to recover the committed state, for various reasons. Log-based CDCs take advantage of this by consuming these logs. It is very reliable. It has no impact on the database performance, and it's very fast. On the other hand, logs are not standardized, so it's often hard to read these data. And it may even change between two versions of one database, which is super annoying. But it's becoming more approachable these days. I will show you a real-world example in a minute. So that was talking, and now let's do something more interesting. How to implement CDC using polling, or how can I call it poor man's CDC. So let's start with our server, which is the service with access to the primary data store. In this example, the store includes data about some rules, but that's not really important for us at this point. And as you may see, the app uses Play as its web server. It's a pretty well-known open source framework developed by Liveband. We have quite a few apps using this in production. In this example, we use Play for implementing the HTTP endpoint, which is hit by clients to get the rules data. You will also recognize that we use Doobie for accessing the database. Doobie is a functional JDBC layer. It is really nice. We use it all the time. DB represents the story here, and the function fetch all rules does exactly what you would expect. Something like select some fields from some tables, kinda. The skip map snippet just transformed the return data to the format expected by the caller. And this is how the client polls the rules. Firstly, it defines server's hostname. This is the address which is hit every n seconds. And here we use Play WS client to do the get call to the defined endpoint. And finally, we update the local state using the receive response. As you can see, this is not ideal. We have to hit the server regardless of if anything has changed or not. Also, we are not able to update the state if the server is not available. Apart from that, it may be quite resource consuming if a lot of clients are hitting the same server, and things like that. So let's try to do something similar, this time as an audit trail / log scraping. We still use SQL as our source, but this time we want to send the rules to DynamoDB, which is queried by the client. And we do it async, of course. As you can see, we introduced a dedicated table for it. This table essentially represents the rules in the same way as the Dynamo table. We could make it work even without this, using the original rule tables exclusively. But it may be quite challenging to handle all the various events and to map them correctly. So we decided to simplify it and accept data duplication and its consequences to limit its complexity. So yeah, the rule data are stored in this field. In reality, we do have a few more columns here, of course, but the point here is it is not a relational model anymore. It is what Dynamo wants it to be. The table is not special by any means. We use to be, again, I just wanted to show you some SQL. It's very straightforward as we are just updating a single table. Just make sure you do this in the same transaction you use for updating the real relational tables, which I don't have here because the slides are not big enough for this. As a messaging layer, we use AWS DMS, which is Database Migration Service. It's a service built exactly for this purpose. It supports various sources and targets, including Postgres and Dynamo, which is what we want here. It is also a managed service, so it's quite easy to set it up. When using DMS, you need to define various selectors and mappings and some other things to make it work. It's not difficult and it's reasonably documented, to be honest, so it should be quite straightforward. So at this point, all the updates are flowing to Dynamo. We just need to access it. To do so, we need to define an ADT. As you can see, it just corresponds to the table definition we have seen before, and call the define get function, which retrieves the rule data using their keys. As you may see, we use Karamo, which is another great library I would like to recommend. And that's pretty much it. This solution scales way better than the previous one. It also decouples the services a little bit, but it's a little bit more work. And now I would like to give you some ideas about various use cases, usually based on what we use CDC for. This, again, won't be an exhaustive list by any means, but I believe it could be, inspireful for you guys. Let's start with the application we just have seen. Essentially, changes from a backing data store, like Postgres or MySQL, are applied to a cache or a secondary data store. Like DynamoDB, Cassandra, Memcache, Redis, or something else. Async approach is usually preferred. We have quite a few implementations of this. In our case, primary store are usually SQL databases wrapped as RDS. And as secondary stores, we use DynamoDB and Redis usually. We have various search apps that we use for almost real-time indexing. And we use CDC pipeline to populate our search backends. That's usually Elasticsearch these days. The next use case I have here is quite opposite. Instead of moving data to caches or search indexes, we can move our data to big data processing systems like Redshift or Snowflake or good old S3 for further processing and analytics, or just as long-term storage. I think this is super important these days as data are key asset for many businesses. It's great to work on a greenfield project. Pretty much, everyone loves that. But unfortunately, that's not always the case. Legacy monolithic apps often need to do more things per transaction. Similar to the example I mentioned before, it may need to write to a SQL database and also update caches and things like that. These are usually called dual writes, and dual writes are well known to be complex and fragile. CDC helps fix these shortcomings by separating these writes. The command query responsibility separation, or CQRS, is an architectural pattern which uses one data model for writing and one or even more models for reading. This can maximize performance, scalability, and it's also like very, very flexible, but it also adds a lot of complexity. CDC can make this more approachable. So for example, writes can be recorded to a database as usual, and we can create streams based on these write events. The streams can be consumed by the services, reading the updates for their read-only views. As I said, this is definitely not an exhaustive list. I'm sure you can find way more applications. Actually, I'm pretty sure we have way more of them just in Disney. But I wanted to give you some samples to inspire you. And as you would assume, there is a bunch of frameworks trying to make our life easier. I will start with a little promo. Its name is PG2K4J, and it was developed and open sourced by us as an alternative to PG2 Kinesis, which we found not performant enough. Conceptually, it is quite simple. There is a running Java process, which reads Postgres' write-ahead log, transforms the data, and uses KPL to write to Kinesis. If you're interested in digging into this, there is a GitHub link in the references section. Maxwell is quite similar. It creates a daemon which reads MySQL bin logs. These are conceptually very similar to Postgres write-ahead logs I just talked about. And it writes to various streaming platforms, including Kafka and Kinesis and things like that. Maxwell was developed and open sourced by Zendesk. Then I have, at this point, well-known DMS. And in the example, I use DMS for pushing data from Postgres to DynamoDB, but it has way broader usages. As a source, you can also use MySQL, MariaDB, Microsoft SQL, or even S3. As targets, you can use various SQL stores, but also things like Redshift, aforementioned DynamoDB, Elasticsearch, MongoDB, and some others. This is a managed service, which is good and bad. And also, it's very tightly coupled to AWS. Spinal Tap is a general-purpose, reliable CDC framework developed by Airbnb. It's built around Kafka, so technically you can use it outside of AWS. And I believe you can use Kinesis too if needed. It supports various data stores like MySQL or DynamoDB. It is a well-rounded CDC solution. I have the links in the end as well. Database is another open source CDC framework, in this case developed by LinkedIn. It is also a general purpose solution. It was developed in 2013, and as far as I know, its replacement is already under development, but it may be still viable for you. And the last, but definitely not the least framework I want to mention here is the BZM. The BZM is again an open source solution, but it's backed by Red Hat or technically IBM these days. The BZM implements unified event model and connectors for various databases. It is built around Kafka and Kafka Connect to take advantage of its great traits like durability, reliability, and fault tolerance. Also, this project is very active, which is always a good sign. As you can see so far, there are a lot of options. Of course, there are more available, so feel free to look around. If you need professional support, it may make sense to go for one of the commercial solutions, which I haven't mentioned here, but that's completely up to you. Always have in mind what makes the most sense for you. In the microservices world we live now, CDC is a widely usable pattern, which I believe everyone should have in mind. I hope this helped you guys to build a little bit more structured view on CDC and gave you some ideas what to think about. That's all I have today. Thank you.